Alright, so a little bit of a review video here then, and a bit of a review lesson over the last few days of notes. We talked about naming organic compounds. Of course, the important things that you should know is that if there are only single bonds between the carbons, it is called a saturated compound, and the compounds end in the suffix "ane". So "ane" at the end means that there's only single bonds. Here are some examples: propane, ethane, hexane. We've drawn those before in class. If a double bond exists, then the name of the compound changes to "ene", E-N-E at the end. And that's an indication that somewhere in the chain there's a double bond. There will exist sometimes triple bonds, and those compounds have yet another name. They end with "ine". So some examples below here are ethyne. Of course, eth means there's two carbons, right? Methane, ethane, propane, butane, and so on. So ethane is two carbons. The "ine" means that there's a triple bond. Now the triple bond will never occur between the carbon and the hydrogen, of course, because hydrogen can't have three bonds, just one. So that triple bond will always be between two carbons. Okay? And that's what ethyne looks like in the structural diagram. Butene, okay, so the first part is BUT, the second part is ENE. And if we take those two together, we have four carbons and we have a double bond, right? Now there is a better way of naming this that you've talked about here, but this is, at least from here, we have, oh yeah, this isn't, in the, okay, so but, B-U-T, right, and then ene. 1, 2, 3, 4, ene means there's a double bond. Okay. We talked about cyclo as well, cyclopentane. And of course, if you have cyclo, that's like circle, right? So a cycle, 1, 2, 3, 4, 5. Cycle means it's in a circle. Penta means it's 5 carbon atoms, and ane means they're all single bonds. Okay, so you took that in your notes as well. Cyclopentene has a double bond. No, this is not the shampoo. That's Pantene Pro V. That's different. Cyclopentene looks like this. And if you don't draw the hydrogens, which you can kind of get away with, you're going to draw a whole bunch of these. And so this is what it looks like without the carbons and the hydrogens actually written out in there. And this is acceptable as well, as long as you understand what's going on. So between these two carbons, we have a double bond, cyclopentene. Okay. All right, so there's a list in the textbook of cyclohydrocarbons, and they are also called cycloalkanes. This term would have been new at this point in the lesson. Alkanes are the general category for single bonded hydrocarbons, hence the ane, see that? Alkenes, double bonded hydrocarbons. Alkynes have some sort of triple bond. And you were asked to do questions 9 and 10 from your textbook. Then we talked about isomers, okay? Isomers. Now, two or more substances with the same molecular formula but having different structures are called isomers, okay? If we have something like C4H10, all right, on page 336-7 you see two structural isomers, and a positional isomer would be like this. So, for example, butene, right? We can have the double bond can be between carbons 2 and 3 in the chain, or between carbons 1 and 2 in the chain. And so, as I mentioned in class, this would be position 1, this is position 2. Now there is no position 3 in butene, because this, if you just flip that molecule around, this would be the same as position 1. So in the notes we talked about this being this position 1, position 2, and this is position 1 again. So there can be 1 butene or 2 butene. You got that? Is everyone clear on that one? I've heard that a couple times right now. So these are something called isomers. When an atom or atoms different from hydrogen or carbon are introduced to the organic molecule, the new part is called a functional group. So hydrocarbons, we've just been dealing with hydrocarbons mainly up to this point, but if you have another group of atoms, that becomes a functional group, very important. One of the functional groups that we will be studying is called the alcohol group. Yes, that's correct, alcohol group. So alcohol has this group of atoms attached to, a carbon chain. So that's the alcohol group. An example, I think I have one right now. Yeah, right here. Okay. So here's the alcohol group, right? Attached to, really attached to propane, right? Methane, ethane, propane, 3 carbons. So we have propane, but we have a functional group attached to one of the carbons. And so this is 1 propanol. Now, prop comes from the 3 carbons. The all at the very end means there's an alcohol group. So the name of this one is propanol. And the reason why it's 1 propanol is because it's attached to the first carbon. The other isomer that could exist would be 2 propanol. We would not have a 3 propanol though, because that would be the same as 1 propanol. Okay. Now here's another way of writing it. You don't get the geometry, the spatial geometry look here with this way of writing it, but that's another way you might see it in your notes. And of course, this O would be attached to the C, not the H, but you'll see it. You'll see it both ways. Okay. A category of stereoisomers resulting from different arrangements of groups around a double bond. Okay. If we're talking about geometric isomers, okay, geometry is sort of how things are spatially arranged, right? And different shapes. So, 2 of the most common geometric isomers are cis and trans isomers. And so we've talked about what this means to the arrangement of atoms in a bond. And next page here. This is, the structural diagram here of cis 2 butene. Now let's just think about this for a second. But is how many carbons? 4. So there's 1, 2, 3, 4. Ene means there's a double bond, okay? And 2 means it's in the second position. So here's the first position, here's the second position, and there's the double bond. Now the cis is the other thing. Cis comes from the Latin term meaning on the same side. So if you look at this, there is spatially we have sort of a electron dense area in bonding coming off this way and coming off this way. It just so happens that this methyl group, and you can consider this a methyl group if you want, a carbon and 3 hydrogens, is coming kind of up in this direction. The same orientation and direction as the other methyl group on the other end. So here's cis, same side, and then of course down here we have trans. So we have the group coming this way, and then the other group on the other end, sort of the other way around. And if we look back at the other notes there, on the previous page, we see that there are definite physical property differences here. Okay, and because of the shape, they have different melting points and boiling points. So they're the same formula, but they act quite differently. All right, optical isomers. So you learned about optical isomers here the other day, and again, sorry, it's a bit small. But optical isomers is another category of stereoisomers that result from different arrangements of 4 different groups around the same carbon. This one's a little bit trickier to envision, I think, especially when you don't have a model kit in front of you. If it's just drawn, but to tell you the truth, I kind of like these versions a bit better. This one is still a bit in my mind confusing because you don't know what directions these are. But if you think about this, this is alphabetical, right? W, X, Y, Z. So around the horn here, W, X, Y, Z is the way they're arranged here. Now, this is the same, right? W, X, Y, Z. This is the exact same. Okay, that's the exact same molecule. It's just like you're looking at it from the other way. So if you think about your hand in front of you, right? So if you put your hand in front of you like this, right? An optical isomer would be like, this is not an optical isomer if you flip it around like this, because it's still the same hand, still the same arrangement. But if I had my thumb somehow put in the middle here, where these fingers are actually out of order from each other, then that's an optical isomer. So just as a I drew here. So just as I drew this right here, this is the same as this one, W, X, Y, Z, right? This one here as well. Let's go to draw. Okay, if we had a carbon here and we had W, X, Y, Z, still the same. Still the same because it's W, X, Y, Z. They're still in the same order. They don't have to go the same direction. They don't have to start in the same spot. But it's definitely different if we have W, and if X is here or here, it's the same as the one above. But if X is over here, that is definitely a different arrangement, right? So W, X, and then let's say Y, Z. So this is an optical isomer, and this is sort of what they're trying to explain here. Okay, so the four groups can always be arranged in two different ways. These isomers end up being mirror images of each other. Right? So if you drew this, with a sort of a line in between as a mirror, right, they would look like optical. All right, so there's a picture of the mirror image right there. It's a better three-dimensional drawing than I could draw. Louis Pasteur discovered that crystals of tartaric acid existed in these two shapes. They're mirror images of each other. Because a person's hands are like mirror images, okay, of each other. I showed you one hand, right? But if you look at both of your hands in front of your face, they are mirror images of each other. And because of that, they're called left-handed and right-handed. Okay, so your left hand and your right hand are different, right? Left-handed and right-handed. So two forms have the same chemical properties, melting point, density, solubility in water, but only the left-handed form was produced by fermentation to make wine. Also, bacteria were able to multiply only when they were fed the left-handed form as a nutrient. So there's some definitely different characteristics, even though they're not physical. And, whoops, I should go back there. Some notes at the bottom. Today, these two forms are called D-tartaric and L-tartaric acid. The letters D and L stand for the Latin prefixes dextro, which means to the right, and levo, to the left. The property in which a molecule exists in a right and left-handed form is called chirality. Chirality. Make sure you have this, right-handed, left-handed forms, chirality. They are chiral forms. Okay, very important. Okay, an example of where this is important in nature, we talk about living organisms, such as amino acids that make up proteins. They have chirality. So here's a little diagram here. This substrate here has a certain kind of shape and a certain form. Only one chiral form is used because it's the only form of the substrate that fits within an active site of the enzyme. So you can imagine if we had, if we had the other version of this, which let's say kind of looks something like, this. This would be my, not very good drawing. But let's say this one came and tried to slip into this keyhole here, it wouldn't work. Okay, even if it's flipped around, you got to remember this is three-dimensional. So there's only certain forms that fit when we're talking about biology. So they're very, very important. And even if we talk about the evolution of life, like you not only have to have the right substrates like this, but they have to be the right hand. They have to be the right chiral form, which just makes the probability of really of evolutionary life coming on its own even that more that more improbable, really. So did you guys do this practice question here in your class the other day? Draw all of the structural isomers possible for the alkane with the molecular formula C6H14. Okay, so you have 6 carbons and you have 14 H's, and there are many different arrangements here. Ignore that C, that was cut and pasted from another document. But anyway, so here are the different versions that you would draw. So hexane, obviously, straight chain, 6 carbons, right? All single bonded. This one right here, 2-methyl pentane. Now notice that if we have a carbon group that's plucked from the end, and it's not attached to the end carbon anymore, this next carbon here, but it's attached to one of the carbons in the middle, then the straight chain, the longest straight chain that exists, would be the what the root of the compound would be. So this is now a pentane molecule. Okay, it's got, yes, it's got 6 carbons, but the longest straight chain is only 5. So even if you start from, even if you look right here, even if this is sort of typical, like the quote end one, you have 1, 2, 3, 4, 5. That's all you have in a row anywhere, right? And so if you look at that, then this is a pentane, and it's on the second carbon, so it's a 2, and the group here, the functional group, we talked about alcohol being a functional group to add it on. Well, a methyl group, CH3, can also be functional, like a functional group, so that's how you would name it. 2-methyl pentane, only single bonds. Okay, that's 2-methyl pentane. Now you didn't have to name them here, but this is sort of what we're learning as well. So if you take another one of these carbons and you attach it to not this carbon but maybe the next one, you might get something like this right here, right? And which one would this be right here? Any guesses? Of all of these listed here, which one would this be right here? Okay, so we're not here yet for naming then, right? Okay, that's good to know. What's the longest straight chain we have? 1, 2, 3, 4. Methane, ethane, propane, butane. So it's going to be some butane molecule. Okay? So we have butane here. Now, did you talk about with the substitute teacher what the 2, 3, what those mean? Okay. We did. You do know what a 2 means, right? It means that the group, the functional group, or wherever the double bond is, or whatever, these numbers talk about the carbons in the chain. And so if we have 2, we know that it's on the second carbon in the longest straight chain. 2, 3 means that on the second and third carbon there's some kind of functional group. There's some kind of group attached to those carbons in the straight chain. So if we count from whichever end, doesn't matter. This is the 1 carbon right here. This is the 2 carbon. This is the 3 carbon. So this name right here matches this molecule. 2, 3. That means on the second and third carbon, there are methyl groups. Now, dimethyl means 2 methyl groups. They're identical. So there's dimethyl. There's a methyl group, CH3, and another methyl group, CH3. And of course, this is all single bonds on the 4-carbon chain, so it ends with butane. So that is something that you need to kind of look over. Maybe you need to, listen to this again, but this is how it goes. Now I'll just do this one more. Obviously, this one right here is which molecule? This one, or this one? 1, 2, or 3? 3. Yes, if you said 3, that's good. You're catching on. Now, why is it 3? Well, butane, so a 4-carbon chain with all single bonds. That's right there. 2, 2. As soon as you see 2, 2 or the same number twice, that means that there are 2 groups on the same carbon. And so we see a dimethyl grouping on the second carbon. So on the second carbon, there's a methyl group, and on the second carbon, there's another methyl group. So that's this one right here. Okay? And of course, this one right here has 1, 2, 3, 4, 5. So that's pentane. And on 1, 2, 3, we have a methyl group. So that's where you get 3-methyl pentane. Okay, so one more practice question. Just draw this molecule here, 1, 3, dimethyl hexane. Okay, did you draw something that looks like that? Yeah? Okay. If you're not told, if there's no indication of which side these carbons would be on, like say if they're both on the same side or opposite sides, you usually draw them, on opposite sides of the molecule if you're not told. So if you have a 1,3 dimethyl hexane, if you ever see this, then try and spread the carbons out as much as possible. But it doesn't really matter because you have this big long carbon chain then on the same side as this carbon, so doesn't really matter. Um, but we talked about cis and trans too. So you did this practice problem the other day. Draw the stereoisomers of cis 3-hexane and trans 3-hexane. So, ene. The 3 means that the double bond is in the third position, right? And so from that double bond, we have cis and trans. You took a look at those, and here they are. Oh, it's a bit tight to see, but on the same side, okay, actually these groups really are on the same side of the carbon. So it'd be like this, C, C with an H, and then the double bond, and we have the C and C with the H here. So really it's these groups are on the same side, and then the trans, you have your double bond there, and then you have your C and C with the H down here, and then the C and the C with the H up here. Okay, so this is cis, and this is trans. Any questions on that? So in this last example, you guys have not done this one yet in class, so we'll take a little bit more time with this one. But the last practice question of this lesson, starting with a single carbon atom. Okay, here's your carbon atom. Draw 2 different optical isomers by attaching the following atoms or groups to the carbon. So remember what optical isomers are? There's 4 groups around a carbon that are in a distinctly different order. There's 2 ways you can do it. So take a moment and draw me the 2 optical isomers. Whoops, no, not see there. Draw the 2 optical isomers given these groups. So there's going to be an H on one, there's going to be a methyl on the other. Okay, there's going to be an ethyl group here, and there's going to be this is a propyl group, 3 carbons. Okay, so draw me the optical isomers. I'll give you a minute to do that. So as an example of 2 optical isomers here, this is what I've drawn. Yours might look just like it. It might look a little bit differently. The big thing is this. We've got hydrogen, and then the methyl, and then the ethyl, and then the propyl. So I started off with hydrogen in the same position. And then remember, the easy way to do this is just to skip across the carbon and put that one next. So switch the next 2 here. So this is what I did. I just did the hydrogen, and then the ethyl group, then the methyl group, and then the propyl. So that's a distinctly different arrangement drawn that way. Okay?